Good afternoon. Welcome to today's heritage lecture by Professor Dani. Um, this is the last day of our iconic week. Before we start, I would request our director, Professor Ravindran, to make a few remarks. Over to you, Professor Ravindran. Professor Ravindran, you are on mute, so we can't hear you.
Okay. Good afternoon, everybody. It's indeed a great pleasure to have Professor Dani with us online on this important event that we have been celebrating for last 1 week called DAE Iconic Week. As we all know that this year is special for various reasons. Not only for India, it's also for, particularly for IMSC. We celebrate 75 years of independence and 60 years of IMSC, and also this is the year for basic sciences, as UN has declared. And really thankful to Professor Dani to agree to talk about mathematical heritage, particularly India's contribution to that, actually. And I request Professor Balasubramaniam to introduce him, because he's not only his colleague and also his close friend, and it will be up to actually to request him to talk about him than me giving introduction to him. Of course, he is well known to most of us. For the younger audience, I thank Professor Balasubramaniam to agree to introduce him. I request Professor Balasubramaniam to introduce him to all of us, particularly younger audience. Thank you. Professor Balasubramaniam.
I think he first needs to unmute. Mr. Balasubramanian needs to unmute his video. Yeah.
Yeah, you are unmute, Professor Balu. You may.
Unmute?
Yeah, you can. You are audible, sir. Please go ahead.
Oh, can I start?
Yes, please. Yeah, we can see you and also hear you. Please.
Okay. Okay. Professor Dani needs no introduction to this audience. He is one among the top mathematicians in India, an authority on ergodic theory, D groups, and their applications to number theory, collaborating with the field specialists. His is really a mathematical family. His wife and daughters are research mathematicians. And for all his achievements, awards and honors came on his way. This includes Bhatnagar Award, the fellowships of the Academy, EWA Prize in 2007, ICM lectures in 1994, and very recently he also became an honorary fellow of the IFR. He has also held many administrative posts, particularly for the development of mathematics. He has been the chairman for the Commission for Development and Exchange of the IMU, and he was also a chairman of NBHM for one term, and has done enough innovative programs under the NBHM. He was also a member and played a crucial role in the Committee for Gender Harmony in TIFR, and he continues to have interest in it and continues to have an interest in it. And now let me welcome him to talk on India's mathematical heritage. Professor Dani.
Hello. Good afternoon, everyone. Let me begin this talk by first thanking Professor Ravindran and IMSC for the invitation to speak as a part of this iconic BAE Iconic Week. And I also thank Professor Balu, my good friend, too, for the kind introduction and also for making it a point to attend this event in the first place. So, yeah, so when the invitation came, I wondered about the topic, what to talk about, and all that. So, I have, apart from mainstream mathematics, in many recent years, I have sort of spoken on various historical topics. So many of the things which come as a part of this segment. But then, given the context of the Azadi Ka Amrit Mahotsav, which we are celebrating 75 years of independence, I thought something like a review of totality of the knowledge, of course, through some glimpses, would perhaps be more fitting for this occasion. So that's where we are. That's why it shows glimpses of India's mathematical heritage. So let me begin with sort of broader perspective. So mathematical knowledge about the past is derived from both indirect sources as well as direct sources. Now, what do I mean by indirect sources? There are various things like the archaeological finds, so something like from the Indus Valley and such other places. When there are temple constructions and so on, where you do not actually see the process of mathematical thought happening, but it is clear from the context that there will be some mathematics would have gone into it. So these is roughly what I would refer to as indirect sources. Apart from this, the other side is the literary side, the scriptures, where India is one of the countries which has endowed with many ancient compositions, writings, not written for a long time, but compositions, we'll call it. So from the scriptures now, of course, they are mostly about not focused on any mathematics or even science. They are actually more about either say about the divine or they are about the practical life, etc. But nevertheless, any literature, as one knows, reflects various aspects of the life of that time. So in the same way, say Ramayana and Mahabharata and so on, you see traces of the mathematics that they now, this is a subject by itself, which I just want the audience to keep in mind, but I will not go much into that. So, for one of the reasons being that this is it tends, I mean, when it sort of tends to be speculative and there will be many uncertainties. And on the other hand, there's a lot more to talk about what we can get from direct sources, what I would call direct sources. Now, here in India, we have a situation, we have a plentiful of mathematical literature, a lot of it kind of unprocessed and lying in various repositories and maybe private homes and in the form of manuscripts, etc. And nevertheless, even what is already deciphered, I mean, the unearthed and deciphered already is something that we can put down as direct sources. So, the direct sources we regarded mathematical knowledge. In this, we don't mean that we are looking for something like an equivalent of a mathematical book or a mathematical textbook here from the past. The very idea of having separate sources and separate compositions for mathematics mathematics, etc., is historically fairly relatively recent. So something like the work of, say, Mahavira in the 9th century or Bhaskara in the 12th century. These are some of the earliest works which are entirely devoted to mathematics. That is not how things happened in the ancient world. Mathematics evolved as a part of various other activities, and it is sort of tied down to the literature or even the philosophical part of that. So according to that, there are sources where the primary theme could be something else. It could be kind of spiritual works, etc. We'll also be going looking at astronomy, but there's a very clear delineation of the mathematics that they knew, and this was primarily intended for dissemination at that time, because the mathematical knowledge that had accumulated, acquired, had to be transmitted further, and it had to be included somewhere, and it came as a part of various other compositions. Like, for instance, you will find mathematics in the books of engineering or architecture, or even, say, economics in our times. There will be some sections where the relevant mathematical parts are given an exposition. Now, again, as a matter of kind of giving a general perspective, I have listed here the variety of sources that we now have available. This list is by no means exhaustive, but these are the one prominent peaks of things that one would rely on. So first, let me go over the list with brief indication of what it's about. Is the first I have listed is the Shiva Sutras. In some ways, it's the most ancient legacy that we have. Shiva Sutras were composed during the Vedic times, a little after the Vedic times. So Vedas themselves are not are primarily about say spiritual things, and also stories about the novels, etc., etc. But the as a part of the process, the yajna, the fire worship, acquired a certain great degree of importance, and as time developed, they had to, because the importance that got acquired, there were a lot of intellectual resources going into that, and then they including mathematical resources, and then some of it is found recorded, and the compositions which are meant to be in aid of performing the yajnas, so the fireplaces, the platform altars, and so on. That is the way of the compositions, Shiva Sutras. We'll say a little more as we go on later. The second thing I have listed here is the Jaina canonical works. So apart from with the Vedic tradition, you all know that the Jainism and Buddhism flourished in India from the middle of the millennium BC to until much later, and even now we have some traces, but now there is a kind of merger of Jainism with Hinduism. So the Jainas, of course, as you again know from your history books, they were against any ritual. So there was no question of anything like the yajnas, etc. But they had they're deeply philosophical pursuits, and they had models of the material world, like the earth is known as the Jambudvipa, is an island in the sitting at the center of a sequence of rings, consisting of alternately of water and land. And on the other hand, they also had a kind of model for how human souls were born, dying, and then the process of it was also associated with certain thing called the uprising, binding, and so on. We'll not go into that. There is still certain philosophical entities, but in the process of that, they realized the importance of mathematics in all thought, and in particular in philosophical thought. I mean, it's also believed that Mahavira, the 24th Tirthankara who rejuvenated the religion, was himself mathematically inspired mathematician himself. The next item I would mention is the Siddhanta astronomy. this is something is perhaps the best known. We all know the name of Aryabhatta, who is the pioneer of the what is called astronomy. And this is an offshoot of astronomy, the interest in astronomy. Astronomy was pursued in India much earlier than the period that we see here, the 4th century to 12th century. However, around the turn of the millennium, there, that time there was a great deal of Greek influence through the advent of Alexander the Great and so on. And later, that interaction was somehow brief. I mean, after a while, the Indian astronomy developed on its own from whatever it took from the influx, and then developed and various mathematical support structures were introduced in India in the course of that. So Siddhanta astronomy involves a good deal of mathematics. So from say Aryabhatta, then you would also have heard of then Bhaskara and so on. And then after that there was Narayan Pandit in the 14th century. So some of that is the astronomy tradition people call it. Kind of outside all the what one may call the mainstream knowledge of mathematics, there is a sort of enigmatic source called the Bakshali manuscript. Now, this is something which it's a particular manuscript which was unearthed in the 1880s. At a place called Bakshali, that is it draws its name from the place where it was unearthed. This is close to Peshawar, about 70 kilometers, 70 miles perhaps. So, and so that contains, it's a single manuscript. We don't get any sense of any tradition and where it fits in the tradition, whether it is before some of the other developments seen in the other things or later, etc. People have speculated. Of course, the mathematical development itself, I think, places it in a certain context, and various other things have led people to believe that it must be from 7th or 8th century. Though when they actually undertook carbon dating of that domain, it led to very confusing results. The various folios seem to come from various centuries. I'll not go more into that detail. So then there was the next item I mentioned is the medieval Jaina works. So I believe all of you would have heard of the name of Mahaviracharya, whose pedagogical influence is kind of well known. The Ganita Sarasangra, which he wrote, served as a textbook for almost 2-3 centuries in wide region in South India. Apart from Mahavira, there is also Sridharacharya, who is somewhat less known in the public. But on the other hand, Sridharacharya is someone who is very well known in the scholarly world. I mean, there is a maximum number of references that in the later works that are seen, including the work of Bhaskaracharya to Sridharacharya. So, and he is from the 8th century, middle of 8th century. But some of these people do not really know much about the precise period or where they were, etc. Now, here last two items. The Kerala School of Mathematics is something. Is a very special event that seems to have occurred. Madhava from Sangama Grama is the originator of this, and this continued as the term school signifies that it continues and as a continuity from teacher to student the next student and so on. That's sometimes more than a student. So the size wise it did not somehow grow, but it had a fair amount of longevity. I mean, Siddhanta astronomy, of course, you see a very long period, but there are lots of gaps that in between. So in each century, you might find some people that now you don't see that kind of continuity. But here in the Kerala school, there is a fair degree of continuity from one scholar to another. And the Kerala School of Mathematics is well known for having produced the work which is very like calculus, akin to calculus. For the people you will argue that calculus started, etc. I will not go into that. However, I mean, there is a good deal of contribution to calculus, and I think that fully will be time doing it. I'll say apart from that, as a part of our heritage, I will also put a mathematics in the pre-independence India. We are sort of reviewing what happened, what came down to us in independent India. So it's also important to have to keep an eye on the works in pre-independent India. Of course, everybody. Trigonometry would of course come to everybody's mind, but there are many some other more names that I'll mention as before. Okay, so now this is of course the last subject, and it would at least take a semester course, if not more, to give a reasonable idea of what we know. But since here the idea is to give a flavor into a few glimpses, I'll go more in terms of the mathematical topics, themes. So I have identified these four as the topics: number systems, arithmetic. Number systems and arithmetic, geometry and trigonometry, algebra, and then analysis. Okay, now numbers, as I think everyone knows, has a long is something of a point of pride in some way for in many respects. So now the decimal system of numeration, the decimal system of numeration and disposal of large numbers has been one of the very distinctive features of the ancient civilization. Now the Rig Veda contains mention of various numbers, and they go up to all the way up to 10,000, and not just these are not just numbers. I mean, 1, 10,000, 10,000, etc. But it involves a very fair degree of sophisticated grammar of composition of the numbers. So 9,000. I'm not record your specific names occurring, but it could be something thousand plus something hundred and so on. And as you see, putting them together, so many hundreds and so many thousands, etc. involves a certain degree of grammar, and this has been studied in some detail by people. Now, yeah, in Yajurveda, which goes a step further, the idea of large powers of 10 seems to have fascinated people. So that's I mean, there are lists. There's a list which goes from 110, that's Eka, Dasha, Shata, etc. I cannot spend time in reading all the Sanskrit names, but you see that it goes up to Parartha, which at that time was actually 10 raised to 12, and it's called Maidathi's list, and the seer who composed that particular Now, this fascination I should emphasize. I mean, we should of course take pride in celebrate what was known, but we also need to know the contours of this. So, while I emphasize that in the case of Rigveda, the numbers of 10,000 came in all kinds of combinations, etc. Here, the later emphasis is largely on thinking of large powers. So, in some way, it is like naming different places and then naming higher and higher powers. So, the list of decoupled terms, decoupled term is the term name for the powers of 10. Up to 10,000, 10 is to 17 appear in various ancient texts, and these include the Vayu Purana and the Bhavish Siddhanta. Bhavish Siddhanta is later reflected in Varahamita's Panchasiddhantika. Now, these names, however, they differ from each other. There is no standardization. The standardization is seen that the work of Sridhar Acharya and then later Bhaskar Acharya, who sort of produced what's served as a standard textbook. So from then on, I think the Parartha is 10 raised to 17. Now, perhaps there was some perhaps. To go into the etymology of this, Parartha, Para is the other god, heaven if you wish, and Artha, so the is is half. So the numbers, the last number that was accorded in the very ancient tradition is named as halfway to heaven. Right? So it's interesting. So now, that is about the Vedic tradition. Now, here in the Buddhist and Jaina tradition, actually one finds even much larger numbers. I think probably the more philosophical people are, they think of larger numbers. So, in Lalita Vistara, which is a philosophical exposition from the first century CE, that is the decoupled terms go up to 10 raised to 53. There are certain series, and the first one goes up to 10 raised to 53. Then there are 8 more series, and finally, in some way, we are talking about a number like 10 raised to 421. So, Mahaviracharya, the Ganita Sara Samgra is actually his names for decoupled terms up to 10 raised to 23. And this was extended by another Jaina scholar called Raja Ditya, 40 terms, etc. And then the record-breaking thing that one sees is this work, Analysis, whose author and period is not known, which has terms up to 10 raised to 96. But these are largely, I mean, in terms of names of powers, there are various combinations, I mean, the more general numbers involving various multiple decoupled terms occurring at various places, like Ramayana, for instance, the army of no, the army thing I meant to say was about the Mahabharata. So, army of Pandavas and Kauravas, etc., are mentioned in the complex terms, but there are not. I mean, these numbers are not really realistic. So there are relatively few numbers where you actually have correspondingly meaningful number associated. Otherwise, in fictional curves, there are numbers which just have a certain only a recreational value. Now, decimal system Indian civilization has a major role to play. Okay, the Indian civilization has had a major role, and with a caveat I have put, though not an absolute one as is often imagined. So, in the development of the decimal place value system of numeration together with zero. So, as you all know, the decimal system that we now use very commonly is something very special. It was not there all the time and it was something that evolved, and somewhere around in the first millennium, somewhere around the middle, more or less, in somewhere. So, just to keep in mind, the comparable systems did exist in other cultures. The ancient Babylonians had a sexagesimal place value system. So they used base 60 for writing numbers. Which also had a zero, but it was limited use, and it's the sense in which it was used in some way was limited. The numbers was also adopted by Greeks. So Ptolemy's astronomical tables also involved that where the gods are listed. That also uses the sexagesimal system together with zero. The Chinese, in effect, had a decimal system because they were not doing in the way that is common in modern places, but it was at least indirectly involved in their counting counting boards. So, okay, we'll not spend more time. The Mayans, on the other hand, were using a system to base 20 visual symbols. Again, the story of zero is something similar, which is it is found in other cultures as well. Some of it I already mentioned. The zero that was used in India is in a way truly in its mature phase. It's more or less like in the way that we use today in our calculations and all. So, and in particular, the as a kind of marker of development, one might also mention Brahmagupta's exposition of arithmetic with zeros. So, in Brahmagupta's Brahmasputa Siddhanta, in the from the 7th century, apart from so there are various statements like when you add two positives, it is positive. When you add zero, the value remains the same, etc. And then when you multiply by zero, you get zero. These are specifically recorded. Of course, one should not imagine that people did not know these things before, but the certain pedagogical goal of recording this and its benefit in transmitting to the next generation is sort of comes to the fore at this point. So, and that's one. So these are some of the features of the Indian heritage, which make a key part of the story of numbers, decimal, and the decimal place value system. Now, the arithmetic that goes with it, the way we calculate, do the basic arithmetic by addition, multiplication, etc., is largely of Indian origin, and then it got transmitted to the Arabs and then to Europe, and that not that they did not have ways of calculating, but they were not same and they're not as elegant or adequate, etc. Now, one of the reasons why the process of ways of calculating did not quite develop there is actually that they were because they were using the abacus and the Chinese were using the counting board. So the mechanical aids made it sort of took away the need for doing things more efficiently manually on pen and I mean whatever equipment that you use. Now, it may also come as a surprise, and which it did when I first came to know about this. Is actually until Laplace's time, almost until the 18th century, people seem to have been very more comfortable using the abacus for the calculation needs than Indian arithmetic. So, and the latter needed the Indian arithmetic needed some conscious promotion at the hands of Laplace and others in France. So there's a very well-known cartoon where there's a competition happening and the Indian arithmetic wins, etc. But it's kind of part of the message that was being carried out that time and not the conviction of people little before that. Okay, so I'd like to remark that we now live in a world in which the two streams seem to have merged, with calculators replacing the abacus. Okay, so now let's go further. So one of the unique features of arithmetic that I would like to emphasize from the Indian sources is this way of calculating square roots. Now, I'll not spend time on explaining all details, but this hopefully brings back to a certain process. So given this number here, it is divided into groups of two, successively, and then you first take the square root, or look at the square root here, subtract, and you make adjustment, etc. And then the way of writing this is the way I we learned in school, and there are some variations which, but basic idea of involved in this was adopted for a long time. The method is usually attributed, it goes by the name of Aryabhata, but comparing with the sutra that was in Aryabhatiya, I feel that the connection with Aryabhatiya itself is rather tenuous. So the Aryabhata's name, I think, came to be associated with it because of the later people giving that name rather than it being explicitly given in Aryabhatiya. Now, in the Siddhanta tradition, it is found in the work of, used elaborately in the work of Bhaskara in the 7th century. On the other hand, it's likely to be of more ancient origin from the Jaina tradition. The Jaina tradition goes back, soon after Mahavira, so the centuries before the first millennium. And there, the Jaina geometry involves square roots of large numbers, and it's unlikely to have been found in any other way. So, this method is something typical, highly Indian, and perhaps quite ancient even before Now, let's go to geometry from arithmetic. The Shubha Sutras are the earliest direct sources of geometrical knowledge, and the Pythagoras theorem and its applications are one of the major highlights of its mathematical contents. The theorem, often even in Western sources, one sees some confusion about this, but I should emphasize that the theorem is actually explicitly stated in all the 4 Shiva Sutras that have been studied, and it is not for right angles. Right, the concept of right angle doesn't come there, but it is in terms of a rectangle. So, given the diagonal of a rectangle, it is and the sides that forms the right angle triangle. In terms of that, the Pythagoras theorem is here. There's also some bit of variation, perhaps, which is worth mentioning. The Baudhayana, Apastamba, and Katyayana Shubha Sutra. So, by the way, I have recalled to you some names. So, these treat it more as a statement about the areas. The area produced by the diagonal is the sum of the areas of the other two sides. So, that's the way they do it. Buddhi is the term used for area. On the other hand, the Manava Shilva Sutra, one of the other sutras that have been studied in some detail, gives the same thing as a formula for finding the length of the diagonal. So, now it tells you that the length of the diagonal is the square root of the sum of squares of the other two sides. So, the perspective also is seen to be the Pythagoras theorem is also used to construct squares equal to sums or differences of squares. So, Shubha Sutra do not contain proofs. However, in the light of some of the constructions involved, it seems reasonable. It's not I'm not saying it only personally. I have known other people who also believe the same is true. That it seems reasonable that they would have known what we would call a visually convincing proof. There is a certain argument you can partition squares in certain ways, etc., and deduce that this is true, and that's the now this is not does not amount to an axiomatic proof. The idea of axioms and fixing a certain set of statements and deducing from that did not arise in India. Now, one of the things that I like to tell about Shiva Sutras is this use of the converse of the Pythagoras theorem. Converse means that if you have a triangle in which sum of the square of one of them is equals to sum of the other two, then the angle is the right angle. So the angle opposite to the largest side is the right angle. Now this inside in this you see a way of constructing a right angle, and this was extensively used in the Hindu sutras. Roughly, here I have indicated it briefly how they do it. So to use the 3, 4, 5 triple, so you take this string and we divide it into two first, divide this part into two, and then we divide this part into two. So I can you see that this segment is in and to this segment is in proportion to 3 to 5. Now you take two poles at 4 units, and then tug this rope. This is a flexible rope. Tug this rope with this mark here. It was called the national mark, and you tug it with that on the plane, so you get this triangle, and that gives you this right angle. And this is how they construct in most of the constructions that one sees. There were a lot of constructions are based on this triple, and similarly also they also used triple 5, 16, a similar idea. Okay, and then I also mentioned that there is a construction of in Upper Sutra, there is a construction of Mahavedi, where a few more temples are also used. Let's go to the circle. So Dharana Sutra describes the way of given this square, how to construct a circle whose area is equal to that of the circle. And the procedure given is you look at this picture. There is, when you take the diagonal component here, it will jut out, and you take this from the extra segment, you take 1/3 and add to this, so that is given as the radius. Now this is not a very accurate method, but it's kind of shows an understanding of how geometrical figures will be approximately transformed into one another. So in the converse direction, so you're given a circle, to find the square, it's not a geometric construction given, but it has method, but a factor by which you have to adjust. So you're given the unit, you take 7/8 of that you add the remaining part you divide by 29 and then divide by 8, etc. Effectively, this formula is given as this number is given as the factor. So I have write it in this way because that's how it is expressed in the Now, interestingly, in the vicinity of this same formula, one finds a formula for square root of 2, which is as 1 plus 1 by 3 plus 1 by 3 times 4 minus 1 by 3 times 4 times 1, 34. And this turns out to be very, very close to the correct value. So, the corresponding values, and you see that it corresponds to they are equal up to 5 decimals. Okay, so now apparently this was done in order to get the converse value this factor. So, however, yeah. Okay, let me go to Jaina geometry. In the ancient world, the ratio of circumference to the diameter is often thought to be 3. This is common to many traditions. But the Jainas were the first to depart from the factors. They adopted square root of 10 as the value for pi, and this value actually had a great longevity. So. And here I have said how so the Jambudvipa, the Earth, is supposed to have diameter 10,000 kilojana, and its the area would be found. We should according to them should be square root of 10 times this, was actually found as the square root of this. And here I have given the very detailed value of that they computed, and it's kind of interesting to see that after so many factors, they also emphasize this. And this is one of the square roots for the method, and there are many instances of square roots, but here is one instance. Okay, the more interesting thing I like about the Jaina geometry is this interesting formula. So here I have the circle and a chord. Let's focus on this part. There is this chord and then the corresponding arc. Now, of course, we know that before in the days before trigonometry, there's no way you could have told what the length of this in terms of this. And here they tell you a formula which is approximate, like okay, the length of the arc, this is the A, which is square root of C. C is the chord. C is this C square is the square of this chord, and to this you add 6h square. This arrow, this is called the arrow. Look at the, you can see the compared with the bow and arrow I mentioned, you can see that this curve should correspond to the arrow, and so the formula is that you take the square of this, add to it 6 times the square of this, you take square root, and that's the arm. Now this is it's clear that this is sort of extrapolated from the Pythagoras theorem. So to compute the length of this path here, that will be 4 times h square, and then if there's an adjustment to this, and the with some perusal, you can see that the correct value for the coefficient here should be 6. Now, the interesting thing is that similar formula, the formula for the arcs was also involved in the work of Heron of Alexandria from the Greeks in the 2nd century, and I'm not going to it here, but the Jaina formula compares favorably in for most values of the angle, not everywhere. But so when the angle is closer to 90 degrees, it's somewhere it changes. But for many values, this formula is gives better results. Let me move on to a later period and more complex formulas. So here, this is Brahmagupta's formula for cyclic quadrilaterals. Now, okay, there's some history which I have written, which I'll skip and focus on the important thing that I want to state. So, the area of in Brahma-Sutta Siddhanta, the area of a quadrilateral is given as a square root of s minus a, s minus b, s minus c times s minus c, where a, b, c, d are the 4 sides of the quadrilateral, and s is the semi-perimeter, which is the sum of the sum of the sides. Now, you see that if you specialize this to one of the sides being 0, then this reduces to the formula that is taught in school. Triangle, and that is known after the Heron of Alexandria, whom I mentioned earlier also. Now, there's a sort of curious and unfortunate historical accident associated with this, and the point is, this formula is actually correct only for cyclic quadrilaterals. Now, apparently, Brahmagupta in fact meant that to be so, but that condition was missed by all subsequent generations of scholars who either reproduced it uncritically and didn't discuss it further, or they criticized it bitterly as a false formula, and it includes in particular Bhaskaracharya, who does that, and without realizing that it's actually valid under certain conditions which was implicit in. Okay, so let me move on to some trigonometry. Trigonometry with angles, for sure, is a Greek origin. But the currently used format of the sine function is closer to the Indian version, in the sense that the use of half chords rather than full chords. So original Greek trigonometry depended on talking about lengths of chords subtended by angles and not half chords. So you do effectively by looking at the sine function. Now, so the term, I mean, they're actually they're not using the units of for the sine function, but a certain multiple of that, which is a bit of a difference from the current practice. But the aspect of taking the half part is something originated in India. Okay, so Aryabhata's guru. Okay, so here is Aryabhata's table of R sign differences. So it's the first trigonometric table you can say in India. Though the table itself may have been there before Aryabhata. It is not in India, but at least it is traced to Aryabhata. Aryabhatiya contains this. Now I have copied here the particular verse from Aryabhatiya which gives the table. These things, Makhi, Bhakhi, etc., they actually correspond to numbers. I will not spend time on interpreting them for you. They stand for this sequence of 24 numbers. So the right angle is divided into 24 equal parts, and for each step, incremental step, with a corresponding number. Now, so here the radius of the circle is chosen to be 3,434. The significance of this number is that when the perimeter is very close to 21,600, which is the number of minutes. So, and then so for the 24th part, it is the corresponding length of the sine is this times the sine is 225, and then the next one is not given by itself, but how much you have to add to this. So that's why there are sign differences. So content myself with just this much detail. So that is the trigonometric table, and rather than the values themselves, there are some differences that are provided. So the table was extended to 1 degree steps only in the 12th century by Bhaskaracharya, and the crucial feature associated with that was to find the third values of 18 degrees and 36 degrees. So then we will skip some more details here. And so apart from the radius 3438, I have said that there are also other radii that were used like 60, and apart from this, so though many of the tables were for the 24 steps, including the later Kerala tables, they are only for have 24 steps. And there are even some tables with fewer steps, so just 15 tables, etc., depending on. So for simplicity, sometimes it is convenient to have fewer steps. One interesting topic about Indian trigonometry is this approximate formula for sine. So they're of course using a certain multiple of the sine function, but in terms of our sine function, which corresponds to saying sine theta is approximately equal to this expression, so theta times 1 minus theta, and divided by 40,500 minus theta times the same factor. Now, that is when the angle measured in degrees. You can of course convert it into radians and have another formula. And this formula is interestingly, the error is just about within 1% for most angles, except for very small angles. If you notice that it went at 0, the limiting values at 0 are somewhat different between the two. But if you are not very close to small angles, then the error is less than 1%. Let me also talk about some algebra and Sorry, I seem to be running out of time, but if permitted, I would like to continue a few more. Okay, so now the solving equations, linear equations, simultaneous linear equations, etc., were quite standard in the many Siddhanta texts, etc. But the more important aspect of the Indian algebra is the Diophantine equations. So these are equations, and this is a method called the Kuttaka method. This is about finding integer solutions of equations for equations like the linear equations like this. So, of course, in terms of real numbers, these are very easy to solve, but to find integer solutions of this turns out to be quite a non-trivial task in some way, and it's related, of course, to the Chinese remainder theorem as well. Recall. But the practice is actually seen to have been much more intense in India, although the modern mathematics, the Chinese remainder theorem has come to be Aryabhatta introduced this method of introduced a method for solving the problem, is known as Kuttaka. Kuttaka is bounding. And it basically corresponds with the process involves. So if you have an equation like this, so you first divide this 487, let's look at the equation 16x minus 487 by equal to 138. So the mutual division, you write this 487 divided by 16 equal 30. Take away, so this 7 remains. Now this 16 you write here, you divide by this 7 and you get 2, subtract 14, and so on. And so in other words, this in other words is a way of reducing, modifying the equation by substituting of variables into equations where the coefficients become smaller and smaller. So once the coefficients are small, you can solve it at some stage and then go back. That is what, from a modern point of view, that is what it is known. But the specific details are worked out and described in the various texts in terms of detail. Another rather important thing that one should know about this topic is the Bell's equation. So this equation, as you know, is the Western tradition is known as Bell's equation: x minus dy square equal to k, where d is a positive non-square number. And this study of this was initiated in India by Brahmagupta in the 7th century, where it is called Varga Prakriti. Varga is the square, a square nature. Brahmagupta introduced a certain procedure which enabled him to do not the general equation, but work out various examples. So I'll talk about some examples later. And the method of solution, which is known as Chakrawala, was introduced by relatively unknown mathematician called Jayadeva in the 11th century, and it was promoted by Bhaskaracharya and his The equation was introduced in Europe in the 17th century by Fermat in the initial, and as a challenge to the English mathematicians and so on. And the initial solutions came from Volcker and Wallis. The equation came to be called Bell's equation, which is again, this is a misnomer even in the European context, and this is apparently based on Euler's misunderstanding of who introduced that. The European tradition was completed by Lagrange gave a solution to the problem, to the general problem, through Lagrange fractions expansions, and which one finds in proofs. The pursuit of this equation, Brahmagupta introduced this identity as well, so which enables to introduce a kind of composition of the different problems, and which is what enabled him to solve. I'm not going to be there. It's called the Bhavana process. So this identity which you can see here it really facilitates attacking the problem. And using that, the Brahmagupta could sort out various examples like 92, 83, etc. So now, the Chakrawala method of Jayadeva and Bhaskara is based on, of course, as one of the ingredients, uses the bhavana position, but the way to proceed with it systematically is involved, and that is Jayadeva's major contribution. Now, notice that there is about 400 years, 400 to 500 years between when it appears that many other people would also have tried this thing. Now, this method, the Chakravala method, actually turns out to be faster in many cases compared to the standard method based on function expansions. It is at least as fast as in all the cases, and is faster. One can identify some features under which it is faster. In terms of modern number theory, it is closer to some work of clouds coming from the Indian math practitioners, of course, content by applying the method, and it always works. And the fact that it always works was later proved by Krishnaswamy with the updated version. The improved understanding is provided by Selenius. Yeah, so right. With that, let me come to the penultimate chapter of what I listed. So this is about Kerala, the school which, as I mentioned, originated with Madhava, lasted for about from 14th to 17th century. I mean, give and take about 2.5 to 3 centuries. Nilakantha, Jeshtadeva, Shankar Variyar are some of the other major figures of the school. One of the important things that is often mentioned is the developed ideas that are germinal to calculus. In particular, they obtained a series expansion of pi by 4 as equal to this, the Leibniz series, and also the corresponding series. So, yeah. The corresponding arctime series, so tan inverse of theta, etc. And also the Newton series for sine and cosine functions. All of these, interestingly, they're all described in verses. So the procedure is also involved in words. So this doesn't, without using some standard principalities, just now, one of the motivations apparently was to determine a value of pi more and more accurately, but this series is not quite useful for that purpose because it's very slowly convergent as well. But they devised a certain way which started quite interesting. By which you can introduce, after n, you can introduce a certain correction term, which is a kind of estimate for what the remaining the tail will contribute. So so end process. And with that, so the correction terms, the successfully defined correction terms that had introduced, using which it was possible to make the calculations faster, and it is surmised, I would say. It's not clear even then how they exactly got some of the values that are found there. I think that bit is still unclear, but it is surmised that the refined versions of the corrected terms were used and to use it to calculate using. So this series you have to take up to a certain state and then make the correction. So and doing it up to 50 terms is supposed to give the kind of values that they gave. It has never been completely convincingly checked, I should say. nevertheless, I mean, one does find values of pi in Kerala literature, which are correct up to 11 decimals and so on. Coming to the modern period, which I would like to be viewed as a part of this heritage. So, as I mentioned, everybody would of course know Srinivasa Ramanujan, but a variety of other names like say a sentence or two. So, this is Ramachandra Lal. He's from the 19th century, actually, before Ramanujan. He is known for his work on this maxima and minima of functions. Shamadas Mukhopadhyay is well known for something for the theorem in geometry. So if you take a planar convex curve, then it has at least 4 vertices. Vertices are like ticks that you can say, and it's known as the 4 vertex theorem, which is kind of very celebrated theorem in that area. There's also Ganesh Prasad. Okay, I'll not go into all my details. So, but particularly he was apart from his mathematics, he was also instrumental in he was very active in the Indian Mathematical Society. He was one of the presidents for a long period with Ananda Rao. Vaidyanatha Swami is well known for is one of the he has a book on topology, which is perhaps one of the first topics, first books on topology internationally, not just India, but it's the book on topology itself. S.S. Pillai is known for his work on Variance problem. We have here Bala Subramanian, who contributed to that problem, continue Pillai's work. Unfortunately, he died young, at the age of 49, accident, air accident. Then T. Vijayaraghavan worked in Modular knowledge theory, and there are numbers known after known as Piso Vijayaraghavan numbers or Vijayaraghavan series program. The youngest I mentioned Meenakshi Sundaram for his work on differential equations. So, though this is kind of not particularly not reasonably known enough, there is a wide tapestry of mathematical work before independence, and on which one could build, and both in terms of research contributions, some of them I mentioned here, as well as the infrastructure which are going to go in terms of the Mathematical Society, Indian Mathematical Society, and various other institutions like the Statistical Institute and the Data Institute for Research, and so these are part of our endowment at the independence. So at the time of the independence in 1947. So in a way, the new chapter does start from 1947. I'll now go into that. So this is a review for the Azadika. We inherited from the past. So thank you with that for your attention.
Thank you, Professor Dani, for a nice, interesting lecture about the Indian heritage. Other questions or comments from the audience? There's something which has been written in the chat box. I don't see any. Are there any comments?
Professor Dani, I had a question.
Yeah.
Arijit Samal here. Could you elaborate again on the Pell's equation a bit for us?
Yeah, sorry. Elaborate. Yeah, okay. Pell's equation is this equation: x squared minus dy squared equals k, the value k is equal to 1 is the objective typically, but starting all the way from Brahmagupta, one does consider this general. So keep in mind both the things. This general thing with both d and k. D is positive non-square number. If it's a square, then things become kind of tricky in some way. So, and k equal to 1 is the aim that you would like to attain. So, and then, yeah, to, so the procedure for this is in great detail. I don't think I'll be able to explain that. It goes. Is that what you wanted, or some question about the historical aspects?
Yeah, whom should we attribute it to first?
Pardon?
Whom should we attribute this to?
Who should it be attributed to?
Yes.
It was introduced by Brahmagupta, and Brahmagupta did two things. So he produce this identity. Of course, once you have the identity, you can you can verify that it is true. But he discovered this identity. It has this. So what does it do? So x1 minus dy1 squared times x2 minus dy2 squared is again an expression with the same type. So here is a new number coming, and with d minus another square of another number. So if you have a pair x1 y1 say k1, for this let's say the value is k1, and for this let's say the value is k2, then you have you can think of this as composition of these two triples. So x1 y1 k1, x2 y2 k2 composes into this number. This number and whatever the value of this. So this is a composition of triples. That is the bhavana. And using bhavana, what happens? For instance, here I have explained. So let's take this case of 92. What one will do is to look at first look at. Don't worry about trying to make this one straight away. First of all, look at if I take 10 square minus 92. So 92 is the value of d. 10 square, if I take x1 equal to 1 and x1 equal to 10 and y1 equal to 1, then I have this value 8. Then what you do is to use this composition. So both of these you take the same, then you get another value. I have not written down, it might take some more time to do the arithmetic, but when you do that, you get a new triple here. But notice that what is going to happen is that this will allow cancellations. Okay? So in effect, you can actually get these numbers, because they involve cross multiplication, etc. They will not be co-prime. So it will be possible to take out a factor and get another number where it is actually small. So therefore, and then just in 1 or 2 steps, actually in this example, one is able to get this by producing more and more such triples, let's say. And doing the cancellation, you can get the value 1. And this was done already by Brahmagupta in various examples. Brahmagupta also notice also that it tells you that once you have one equation, one solution for this equation, you have infinitely many of them, because if both of these are 1, then this naturally has to be 1. So it will another solution, and you can see that successively the successive solutions that keep producing are going to be larger and larger. So there are infinitely many of them. So this part actually goes back straight to Brahmagupta. Then there are various people. So there's also, I mean, I only mentioned Jayadeva, but before that, Sridhara, for instance, discussed the rational solutions of this and some applications of that to writing integer solutions. So it's a lot more work. So Brahmagupta and Sridhara, then Jayadeva, of course, I mentioned as the person who introduced the Chakravala method, and then Bhaskaracharya as the expositor. So this is some of the history. Now in Europe, it came, the whole thing came much later. But in a way, however, you should also keep in mind that for d equal to 2, which is the smallest case in some sense, one can trace it to the Greeks. In the case of the Greeks, they were interested in the equation x square minus 2y square equal to 1, and there's a method by which they actually solved it, which is not and their method doesn't generalize to, I mean, it not in any natural way to general t. So if you think of x square minus 2 as y square equal to 1 as a separate thing and formulate the problem in this term, then it is Gupta is the originator of that, and Jayadeva is the one who given a general solution in the general case. And in Europe, as I said, it started with Fermat, and Lagrange was the one who put it in systematically through vector fraction expansions.
Thank you very much.
Any more remarks? Any more questions? There are, yeah, please.
Yeah, there are no questions, Professor Balu. Please go ahead.
Yeah. Now let's thank the lecturer once again for a beautiful lecture. Thank you. Now I hand over to the director of IMC.
Professor Ravindran?
Thank you. This is really wonderful to have you. I really thank Mr. Dani for agreeing to this. I want to invite him to our institute when everything is possible. Yeah. Thank you very much.
Thank you.